Let's make the explanation of Go's garbage collector more interactive. Imagine yourself tuning the GC settings based on different scenarios to optimize your application's performance. 1. Default configuration. Balanced performance. You're building a web server with a moderate number of requests. The default GC setting, GOGC 100, works perfectly here. Why? The GC triggers when the heap size doubles, balancing memory usage and CPU overhead. Outcome: your server runs smoothly without frequent GC interruptions. 2. Low latency. Frequent GC cycles. Imagine you're working on a real-time gaming server where even a tiny pause could ruin the user experience. You lower GUT to 50. Now GC runs more often, but with smaller heaps, reducing pauses to a minimum. Result: the game runs seamlessly and your players stay happy. 3. High throughput. Less frequent GC. What if you're running an in-memory database processing millions of records? You prioritize throughput over latency. By setting GOGC equals 200, GC runs less frequently, allowing the heap to grow larger before collection. Effect: fewer GC interruptions, faster data processing, and optimized performance for memory-intensive tasks. Tatter 4. Manual GC triggers. Predictable cleanup. Let's say you're handling batch jobs that allocate lots of memory but have predictable workloads. After processing each batch, you explicitly call runtime.gc to clean up memory. Why? This ensures the system stays clean and ready for the next batch without unnecessary GC during processing. 5. Dynamic adjustments. Adapting to workload. Now, think about an application with periods of high activity and idle times, e.g., a ticketing system. During peak hours, increase GOGEG 150 for better throughput. During idle times, lower GOGC E50 to conserve memory. Dynamic adjustment. Use debug.setGC% to switch between modes at runtime. 6. Debugging and profiling. See behind the scenes. You notice your application sometimes lags. What's the culprit? Enable GODEBUG gtraces1 to monitor GC activity. Use cheap pprof to profile memory usage and identify allocation hotspots. Outcome: you discover a part of your code allocating too many objects and optimize it to reduce GC load. 7. Optimization strategies. Reduce GC load. Want to reduce GC interruptions altogether? Reuse memory. Use sync.pool to cache frequently used objects and reduce heap allocations. Avoid heap pressure. Keep variables on the stack by limiting their scope to functions. The big picture. Go's garbage collector is like a gear system in a car. Depending on the road, your application, you can shift gears, adjust G to balance speed, memory usage, and latency. With the right tuning, you can make your Go application run like a well-oiled machine. Now, where will you start tuning your application's GC? Low latency? High throughput? The choice is yours.